So we've been talking about the Laplace transform, and we've been transforming functions from the time domain t over to the frequency domain s, and then we started looking at bringing them back. One of the major algebraic tools to bring them back is partial fraction decomposition. So once again, if you look on the Blackboard side, I uploaded a couple videos to review that process if you need it. So hopefully we're all dialed in on our basic formulas moving from time to frequency and our basic formulas moving backwards. And now we're going to talk about what the Laplace does to derivatives, because after all, that's what the course is about, is solving differential equations. And as we'll see with Laplace transforms, more specifically, we're going to be solving initial value problems. We'll need to know initial values for us to figure this out. And this is why right here. If we look at the theorem that transforms derivatives, it involves not only the transform of the function, but also the initial value. Okay, so here, under this context here, the Laplace of y of t, that's our capital Y of s. So basically it says if you want to transform the derivative of y, it's s times the transform of y minus the original function y evaluated at 0. So this is going to be something with s's in it. This is going to be a number. Okay, so this is the initial value. So how does this work? Well, anytime we go back to try to prove a property of the Laplace transform, we're going to go back to the definition. So if I look at the Laplace transform of anything, by definition, it's the integral from 0 to infinity of that thing times e to the minus st dt. And if we want to get this in terms of the Laplace transform of the original function, so the Laplace transform of the original function y, that's the integral from 0 to infinity of y of t e to the minus st dt. So the first thing we got to figure out is how could I get the derivative out of here and the original function back in. And the way we'll do that is we'll do that by parts. We'll do integration by parts on this. So let's take a look at the antiderivative here, y prime of t e to the minus st dt. And if I want to get from y prime to y, then I need to integrate to do that. So I would select the dv here to be y prime of t dt, so that my v would be y of t, which means our u for the integration by parts would be e to the minus st. So my du would be the derivative of this with respect to t, okay? Because remember, we're integrating with respect to t, so we're treating s as a constant. So what would the du be here? If I'm letting u be e to the minus st, what would the du be? Yeah, good. We'd have a minus s e to the minus st dt. And then we can do the old integration by parts. uv minus the integral v du. Oops. So that would equal y of t e to the minus st minus a negative v du. So this would be minus the integral of minus s e to the minus st y of t dt. And so I can take that minus out front. It's going to turn into a plus. And so I get the integral, and we'll go ahead and put the limits back on here, 0 to infinity of, y prime of t e to the minus st dt. That's going to be y of t e to the minus st from t equals 0, and then as t goes off to infinity, plus, and now I can bring that s out front, s times the integral from 0 to infinity, and then I'll write this as y of t e to the minus st dt. Okay. And sure enough, here comes our Laplace transform of the original function. So this is our Laplace transform of the original function y, which we're going to call capital Y of s. And so I'm going to use these bars here to indicate a capital Y. And now we just got to figure out what we're going to do with this piece. So let's think about what has to happen here. So if I'm looking at y of t e to the minus st from t equals 0, and then as t goes to infinity, we have to think what's going to happen as t goes to infinity of y of t e to the minus st. We don't know what y of t is. But when we take these Laplace transforms, we need to have this piece go to where? In order for that integral to converge, we need to have the exponential here be an exponential decay, and it needs to overwhelm the original function y of t. So this is what we call, we say that y of t is of exponential order, means a decaying exponential will eventually zero it out. Okay? So if you look at all the Laplace transforms we've done, this part of the integral always goes to 0 because eventually the exponential is going to overwhelm it and trounce it. And so this would be 0 minus what you get when you plug in t is 0. And so you get that minus y of 0. And so this piece goes to minus y of 0. That piece goes to the s times the Laplace transform, and that gives us our property. Right. So this is why we're looking at specifically initial value problems. If we don't have initial value problems, then we just have these constants. And then we can still solve the initial value. We can still solve the diffie-q, but our answer is going to have the initial values in there. So what's interesting about Laplace transforms is, you know, the difference between what we're doing here and what we did before. Normally we would have these C1 and C2s. We would solve the differential equation and then impose the initial condition to get the values of the constants. With Laplace transform, it should all come back at once. So let's take a look at this example here. I want to solve this initial value problem. Once again, our independent variable here in Laplace transform is going to be t. So if we're given this initial value problem, we're going to use the Laplace transform to move this differential equation over to the S domain where it's algebraic. We're going to solve the algebraic equation, and then we're going to use the section 8.2 inverse Laplace to bring it back. And this is going to be all we're working on for the rest of the chapter. The next thing we'll talk about, probably not tomorrow, but probably on Thursday, is we'll start incorporating different functions into the mix here. But this is the main idea of the chapter. So y prime minus 6y equals 3t. Y at 0 is 2. If you want a nice little review, you might spot this as a linear equation. You could solve this actually going back, way back to the second day of class or the end of the first week of class? Section 2.1, you could actually solve this. This is a linear equation. But we're going to use Laplace transform. So our first step is to Laplace everything over. And so once again, the way I'm going to denote the Laplace transform of our solution function little y of t is I'm going to use these bars, big Y. And I'm going to suppress the dependence on s so we don't think we're multiplying there. So I'm going to use our property we just learned here. The Laplace transform of y prime is going to be s times the Laplace of y minus little y at 0. The Laplace transform is linear, so the Laplace of y prime minus 6y is going to be the Laplace of y prime minus 6 times the Laplace of y. And that's going to be 3 times the Laplace of t. Okay? So I'll just fill in now what we got. So s times y minus. Y at 0 is 2. That's given to us there. Minus 6y. And now I'm going to take 3 times the Laplace of t. So we go back. Think back to last week. What's the Laplace transform of t to the first power? Yep. So it'd be 1 factorial, which is 1, over s to the 1 plus 1. That's s squared. And now what I have is I have an algebraic equation for capital Y. All right, so we're going to get all the capital Y's on one side and everything else on the other. So we'll be able to factor that capital Y out there. So I've got S capital Y minus 6 capital Y equals, I'm going to add that 2 over. So it's 3 over S squared. It'd be plus 2. Now I want to solve for Y. So to solve for Y, I can factor it out. Oops. I get S minus 6 times Y is 3 over S squared plus 2. Then I could divide through both sides by S minus 6. So now I've solved the algebra equation for capital Y. Capital Y being the Laplace transform of the solution to the initial value problem over in the time domain. All right? So now what I have to do is I have to bring it back. So I'm going to take the inverse Laplace of both sides. So we Laplaced it over to the frequency domain. Now we got to bring it on back. So I have to take the inverse Laplace of the left-hand side. Okay. Now at this point, it kind of comes down to a couple of different things. Some students like to get a common denominator and then break things up into partial fractions. Or some students like to do partial fractions and then simplify before they take the inverse Laplace. Eventually, we're going to be breaking these up into parts. So my recommendation is, this 2 over s minus 6, that's set. Let's take a look at the 3 over s squared minus s minus 6. We have to break that down into partial fractions. So what's the form of the partial fraction decomposition here? What kind of little denominators will contribute to this big denominator? Yep, good. S squared, and s minus 6. So we'd have some constant over s plus, and because this is s squared is a repeated linear factor, right? Technically this is an s minus 0 squared. I just need a constant over s squared there, and then a constant over s minus 6. And then we can, we could heavy side some of these away if you watch the heavy side video. If not, we can always clear denominators, multiply both sides by that denominator. We'd add a times s squared times s minus 6. The s would cancel. We'll be left with 1s, s minus 6, plus b times the s squared would cancel, plus c times the s minus 6 would cancel. And now we can try to take advantage and get some cheap answers here. We can cheese it. What would be a good value for s to plug in to cheese out at least one of these coefficients here? What would be a good value of s to plug in? S equals 0 would be a good one. So once again, on the left-hand side, you plug in s equals 0, you're just going to get 3. But on the right-hand side, you're going to zero out the first term and the last term. You'll just be left with b times 0 minus 6. So what's that get us for b then? Yep, negative 1/2. What would be another good value of s to plug in? It's going to zero out some of these terms. Yep, s equals 6. You plug that in, that'll wipe out the first two terms. We'll have a 3 on the left-hand side. That's going to be c times 6 squared. So that'll give us c as 3 over 36, which is a 12th. So that means all that we have left to find is a. And the way we can find a is by equating coefficients. So let's go ahead and look at the coefficients that would involve a here. I guess we can just write it above here. So if I multiplied this out, I would have as times s, so that'd be as squared minus 6as. So a would be a coefficient of s squared and s. Here we'd have a bs minus 6b. And here we'd have a cs squared. So if I look, I could either look for coefficients of s squared. That involves a and c. I know what c is. Or I could look at coefficients of just s. Either way, I should get to the same answer. So let's look at the s squared coefficients. On the left-hand side, there's no s squared term present, so that's going to be a 0. And on the right-hand side, I get my as squared plus my cs squared. But I know that c is 1/12. So that's going to give me a is minus 1/12. Okay. And once again, you could have gotten to these answers by just equating coefficients for s squared, s, and the constants. All right, you would have still gotten to these, but If you can find cheap things to plug in to make your life easier, then by all means do that. All right. So here's what we've got now. We've got that 3 over s squared times s minus 6 is equal to minus 1/12 over s minus 1/2 over s squared plus 1/12 over s minus 6. So now I can plug it, I can put this back over to here. My y of t is the inverse Laplace of all of this. And notice I got that 2 over s minus 6 there as well from before. Where did it go? Uh-oh, I lost it. So, feel free to combine these now, or we can combine them after we bring them back. It really doesn't matter at this point. So we'll just use the linearity here. So this is going to be minus 1/12 inverse Laplace 1 over s minus 1/2 inverse Laplace of 1 over s squared. And then it's, this is 2 1/12, which would be what? 25/12, is that right? Inverse Laplace of 1 over s minus 6. So here we go. Minus 1/12. What's the inverse Laplace of 1 over s? Yep, that's just 1. Minus 1/2. What's the inverse Laplace of 1 over s squared? That's just t. And then plus 25/12 inverse Laplace of 1 over s minus 6. It's e to the 6t. And that's it. There's no having to plug in the initial condition to figure out constants because that's already been accounted for. So it's just written the other way. And once again, I encourage you, just good review here for what's coming up at the end of the course here. You can hit this with section 2.1 stuff. Use your integrating factor. You would have some constant involved here, and then you would impose the initial condition to help get you that constant. Or you could do chapter 5 on this. You could do chapter 5 on this. You could solve the homogeneous equation using your m's. You'd get your m minus 6 is 0 here. And then once you get that, you can do your undetermined coefficients. These are 3 different ways to get to the same answer. Okay. Any questions on the process here? Step 1, Laplace. Step 2, solve the algebra equation. Step 3, inverse Laplace. Right? That's how we're going to be solving these. And like all good things in calculus, you're going to spend most of your time doing algebra stuff. Okay. Okay, what if we have higher order derivatives? We spend a lot of our time in Chapter 5 and Chapter 6 looking at second-order equations. Second-order equations, they come from Newton's second law, or they come from those Kirchhoff laws. So they're important. So how do we handle second derivatives? We know how to handle first derivatives, right? The Laplace of first derivative is s times the Laplace of the original function minus the initial condition y at 0. How would I handle a second derivative? Well, you got to remember that the second derivative is just the derivative of the what? First derivative. So you just take the Laplace of the first derivative. So this would be the Laplace of the first derivative minus the initial value at the first derivative. That's just applying this formula to the first derivative. And now, excuse me, it's s times, I forgot the s. It's s times the Laplace of the first derivative minus the initial value of the first derivative. And now, I take the Laplace of this. The Laplace of y prime, that's going to be s times the Laplace of y minus y at 0. And so I'm going to get s squared y minus s times y at 0 minus y prime at 0. That's how you would Laplace the second derivative. And if you had a third derivative, you would just keep going, right? And you'd see the pattern evolve pretty quickly. Right? See the pattern evolve pretty quickly. Right? So we just iterate that formula we had earlier, and that's our equation. So now notice, once again, we need an initial value problem. Notice that the function y and y prime, we need to know what they're doing at 0. Okay, that's why we're looking at initial value problems. Okay, so here's our Laplace of the second order here. So let's take a look at our next equation. This is something straight out of chapter 5. This is right out of section 5.2 actually. Y double prime minus y prime minus 6 is 0. Y at 0 is 1. Y prime at 0 is 0. So the first step is to Laplace it over. And we remember that the Laplace is linear. So if we take the Laplace of y double prime, we're going to get s squared times the Laplace of y minus s times y prime at 0 minus, s times y of 0 minus y prime at 0. So this is all coming from that first term there. So that's the new thing we just did. Minus the Laplace of y prime. So let's go ahead and use parentheses here. That's s times the Laplace of y minus y of 0 minus the Laplace of 6 equals the Laplace of 0. Now we plug in what the y at 0 is and y prime of 0. So I get s squared y minus s times y of 0. Y of 0 is 1. So minus s minus y prime of 0, which is 0, minus s times y minus a minus y of 0. So it'll be minus a minus 1, so that's a plus 1. Minus 6 over s equals 0. And as promised, we now have a linear equation in the variable capital Y. So we're going to solve that. Going to get all the capital Y's on one side, add everything else to the other side. So we're going to add the S over, subtract the 1, and add the 6 over S over. Now I can factor out the Y here. And then divide both sides. And now I've solved for the transformed function y. So now it's time to bring it on back. Any questions on getting down to the transform function here? So the function we're after, little y of t, is the inverse Laplace of big Y. So little y of t is going to be the inverse Laplace of all of this. S minus 1 over s squared minus s plus 6 over s times s squared minus s. Okay. So let's take a look at what's going on here. If you started partial fractions on the first term, what's the first step of any partial fractions? The first step is always to do what? So what's the first thing you always do when you start into a partial fraction thing? Yep, you factor that denominator. And in this particular case, boy, this is nice. That just cancels out. So that one's done. Okay? And now we're looking at the second piece here. We've got a little more work to do. Oops. So now we're back to the same, more or less the same decomp we had before. So I got an a over s plus a b over s squared plus a c over s minus 1. Clear denominators. Or use Heaviside, whatever. Pick some good values of s. What would be the good values of s to plug in here? Yep, 0 and 1. You plug in s equals 0, you get the left-hand side is 6. That's going to be b times 0 minus 1. That's going to get you your b. Plug in s equals 1. Left-hand side gives you 6. The right-hand side is going to give you a c times 1 squared. C equals 6. And once again, to get that last one, A, equate coefficients. Looking at the s squared coefficient, you've got none of them on the left-hand side. On the right-hand side, you got A plus C. So that means A is going to be the opposite of C, which is minus 6. Okay. Or you could heaviside through B and C. It's up to you. Whatever you do is fine, as long as you write down what you're doing to get these coefficients. All right. So now we've got, oops. Here we go. So this is what we need to do, our y of t here. Y of t is inverse Laplace of, we got our, well, s minus 1 over s squared minus s. That's just 1 over s. Plus 6 over s squared minus s. We worked that out to be negative 6 over s. So I guess I'm going to put a minus there. Minus 6 over s squared. Plus 6 over s minus 1. So once again, let's take this opportunity to combine these. And so y of t is, once again, using linearity, minus 5 inverse Laplace 1 over s, minus 6 inverse Laplace 1 over s squared, plus 6 inverse Laplace 1 over s minus 1. So now we do the inverse Laplace. So what's the inverse Laplace of 1 over s? That's just 1. So that's minus 5 times 1. Minus 6 times, what's the inverse Laplace of 1 over s squared? T. Good. And finally, what's the inverse Laplace? E to the 1t, or e to the t. And there's our answer. So once again, back in chapter 5, we'd have to plug in the m's. We'd get the two-parameter family of solutions. Then we'd impose the initial conditions. Here we get it all in one fell swoop there. What did I screw up? So I must have really botched that. What did I do here? Did I write it down correctly? Y double prime minus y prime minus 6 is 0. All right, got my s squared minus sy of 0 minus y prime of 0. Oh, I dropped the y. Thank you. Yeah, I did write it down wrong. Yeah. So this is, yeah, so this isn't the solution of the one we had. Yeah, this would have been, thank you. Yeah. Yeah, so that's, yeah, this is the solution to this equation right? We just solved a different one. So yeah, I'll just make a little note of that. This solves y double prime minus y prime minus 6 equals 0. Not 6y. I forgot about it, yeah. Yep. It's the same procedure, though. Yeah, so go ahead. So the only difference here would be you would have all your stuff, then you'd have a 6y down there. Okay. Which actually would make the partial fractions a little easier. Okay, let's take a look at this one, number 5. Once again, this is something we could do right out of chapter 5. Get the complementary solution, guess the particular solution with undetermined coefficients, and then apply initial conditions. Let's go ahead and Laplace this over. So once again, so we will Laplace the y double prime. We're going to get our s squared y. Take home problem 1 with the for what? Take home 11? No, you don't. No, you can just use chapter 6 on that. I mean, you could if you wanted to. You could, yeah. If you haven't started, yeah. But this is really a chapter 6 thing. So yeah, it's up to you. Yep, everything. It's all good. Whatever you want to do, yeah. So let's see what we would get here. We would get our s squared y minus s little y prime of 0 minus sy of 0 minus little y prime of 0 minus 4 times Laplace of y prime sy minus y of 0 plus, and then this is 4y, so it's going to go to 4 capital Y. Laplace of 5 will be 5 over s. So this will give us s squared capital Y minus sy of 0. Now for us, y of 0 is 0, so that's going to just completely cancel that out. Minus y prime of 0, which is 1. Minus 4 times s times y, so minus 4s y minus y of 0, which once again is 0, plus 4y equals 5 over s. I'm just double checking here. Okay. So now we get all the y's on one side and move everything else to the other, and we can factor the y out. So we're going to have an s squared y minus 4s y plus 4y equals 5 over s plus 1. So we're going to get y equals 5 over s times s squared minus 4s plus 4 plus 1 over s squared minus 4s plus 4. So at this point, you'd go in and do your partial fraction stuff. you would factor this. That would be an s minus 2 squared. So you get your a over s plus b over s minus 2 plus c over s minus 2 squared. This piece is already, when you go to factor it, okay, and we're almost out of time. But you find your A, B, and C, and then you would Laplace them back. And just something to remember here, folks. This is really the only new thing here I'm trying to remind you of. How would you do the inverse Laplace of 1 over s minus 2 squared? What property would you have to use there? This is one of the properties we practiced at the end of last week. Yep, you need that shift. So you see you got an s minus 2 in parentheses, so you can pull out that e to the 2t inverse Laplace 1 over s squared. So that's going to come back as a t. So it would be t e to the 2t would be coming out of those terms. Okay, but I'll leave that to you. Once again, it's the same old rinse and repeat. Partial fraction decomposition, bring it all back, and you should get that. Okay. So I guess if you wanted extra practice, you can finish off this problem and then go back and not forget the y on this one. And those are a couple practice. And then, of course, you've got the book homework you can start working on as well. Okay. Tomorrow we'll go back and tackle this one. All right. This will probably take a good half hour or so. And yeah, as Zoran mentioned, you do have technically all the tools if you want to tackle the take-home with Laplace. That's totally fine. Or you could use the stuff we did in Chapter 6, which was really the stuff we did in Chapter 5. Okay. So as always, I appreciate you tuning in, folks. Have a great rest of your day, and we'll see you tomorrow.